All right, stats kids. My voice is really crackly right now, so I apologize for this video in advance. Yesterday we started section 10.1, and we ended finding the correlation coefficient R, and we did that by using Google Sheets, or I showed you how to do it on your calculator for some of you. And we found that our R value was 0.795 for just these 5 data values. Okay, so that means that our correlation is 0.795 between chocolate consumption and Nobel Prize winners, which you wouldn't normally think that those two things were correlated. But they're saying that they do have somewhat of a linear correlation, not very strong, but 0.795 is, the number that we're dealing with for the R value, okay? I'm going to wait to do example 2 and example 3 with you in class because those are, shows you how to use these two different formulas here to find that correlation coefficient R. And it's a big long table that you have to do, and so we're going to kind of go through that real quick tomorrow. But skip down to example 4, and example 4 is just kind of shows you a quick check of how you determine what is a good enough R. So we said, like your R value has to be between -1 and +1. And the closer it is to -1 or the closer it is to +1, the better, because that shows a really strong relationship. Strong and strong. A weak relationship would be like anything close to 0. 0 is going to be weak in the middle. So strong and strong for -1 and +1. But where is that cutoff mark? So if -1 is here, +1 is here, where is this cutoff mark located to tell me what's good enough and what's not? And the way that we kind of look at that, you guys should have a chart that my sub gave you. It's a little skinny chart. I think I have it like cut into like thirds of a sheet of paper even. It's a really skinny chart, and this is kind of your quick check of how you determine what's considered to be good enough, okay? So in example 4, they kind of switched everything up on us. We're still doing the Nobel Prize winners and chocolate consumption, but now they're taking us to the original table 10.1, which is in the back of your book. You don't have to look at it. But in table 10.1, it has 23 pairs of data values rather than just the 5 sets that we had up here. They only had us do 5 up here so that we didn't have to get overwhelmed with 23 numbers all at once. But in section 10, or in this problem, they're giving you all 23 pairs, and they say all 23 pairs have an R value of 0.801. So that's why this R value is not the same R value as what we got yesterday. 0.795, those are pretty close, but that's why those are different, okay? So the R value that we're comparing to is 0.801, okay? And the quick check to determine what's considered good and bad, the cutoff mark, is determined by this table. We have 23 pairs of data, and so our N, this does not go by degrees of freedom. It goes by the exact number for N. N is 23, but we don't have 23 on the table. It's somewhere between 20 and 25, and we're going by a significance level of 0.5. If you saw that up here, 0.5 significance level. So our number that we're cut off is going to be somewhere between 0.396 and 0.444. Okay, so they went ahead on this diagram here. They're saying 0.413, and I don't think they necessarily took the average of those numbers to find that one in the middle. Excuse me. What I think they actually did was they used technology to figure out where 23 exactly would live. So they came up with the number 0.413. What I always tell you to is round down, which is up in the table. So we would actually use the value for 20 because we don't ever want to assume more confidence than we have or assume more accuracy than we have. So I would use 0.444. They got the exact value, which is 0.413. So I'm going to cross this out and put 0.444 because in the end, it does not matter because our number, 0.801, still is going to live in the correlation section. So normally we would not assume that chocolate consumption and Nobel Prize winners would have a linear correlation, like the more chocolate you consume, the more the higher chance you have of winning a Nobel Prize. That's kind of how that works. But they are saying in this case, there is a positive correlation between the two. As one increases, the other one increases. Oh my goodness. Now, that does not necessarily mean, if you go on to the next page, that does not necessarily mean that one causes the other one to happen. So I can't, by consuming as much chocolate as I want to, that doesn't increase my chances of winning the Nobel Prize. It's just saying that both of those things are correlated. The more chocolate you consume, it just so happens the more Nobel prizes or your higher chance of winning a Nobel Prize is. Okay, let's go to example 5 here, which talks about the value of r squared, which we talked about yesterday. And it says if our value of r is 0.801, r squared is going to tell you the percent of data that lies on your line, which they write as the proportion of the variation in y that is explained by the linear relationship between x and y. Basically, it says the proportion or the percent of values represented by a linear relationship. So it's like the percent of data values that live on the line that I would draw on my graph, okay? So if our r value is 0.801, our r squared value, if you square that value, is 0.642. And we kind of came up with that close to the same number yesterday. So that would mean that 64.2% of my data values would be linear, have a linear association with one another. So not real great, but is enough to say that they are a linear relationship because that's what we came up with here, okay? Now, this was a quick check. We're going to go down and do an actual hypothesis test to confirm or figure out if that is actually true. So your hypothesis test, which is what you're going to be doing in your homework assignment, every null hypothesis, alternative hypothesis will be set up like this, starting with, they use the variable p. I don't know what P really stands for. I don't know why they use P other than like they didn't want to use R and they didn't want to use T because those were already used. So they're using P, and they're saying P equal to 0. Maybe they're talking about like the proportion. I don't know. When they talk about, let's see, what proportion of variation? I don't know. P equals 0 means that there is no correlation because on our -1 to +1 chart, the closer it was to 0, this meant no correlation or a weak correlation. So if it's equal to 0, then that means there's no correlation. We set up our alternative hypothesis to say that it's not equal to 0, which means there is, yes, a correlation. So if it's over here close to 1 or over here close to -1, there is, yes, a correlation. Okay, your test statistic T is found by doing this formula. So you take your r value divided by the square root 1 minus r squared over n minus 2. Excuse me. And you use n minus 2 degrees of freedom this time, not n minus 1. So keep that in mind. When you're doing your bell curve to figure out what these numbers are, since our test statistic was called T, you're going to use the T chart, the one that we used when we were doing means. It looks like this. This is your black and white chart. It's the T distribution. So we're going to use that table to figure out where these cutoff marks are at, right here and right here. Okay, so let's run this hypothesis test and let's see what we get. Use the paired data on page 469, you don't have to look at that, to conduct a formal hypothesis test of the claim that there is a linear relationship between the two variables. So our claim is that there is a linear relationship. So claim actually goes with the bottom one, that there is a correlation. All right, use the 0.5 significance level with a p-value, p-value method. I do critical value method. Okay, so that's the one thing that is different. All right, excuse me. All right, Using this formula up here, we've got our R value was 0.801. Let me check that. Yep, 0.801. Square root 1 minus 0.801 squared over n minus 2. And, oh shoot, I should fill our n in. N was 23. We had 23 pieces of data. Okay, so I can simplify this if I want to. This will be 21 on the bottom. And when you type that all into your calculator, practice typing that in, you should get 6.131, which is a pretty significant, like significantly high level. I'm guessing we're going to be like all the way out here on our chart. But let's figure out what these two cutoff mark values are. We do have two tails because it is an equal to, not equal to. And our significance level is 0.05, so that means we have 2.5 in each side, just like normal. Okay, 95% in the middle. And our degrees of freedom was n minus 2, remember that. So 23 minus 2 means I have 21 degrees of freedom. Okay, so I want to look up on the chart 21 degrees of freedom at 95%. And, oh, I'm in the wrong spot here. Let's do 21 degrees of freedom is this row right here. And 95% is the middle row here. So I'm looking at 2.080. 2.080 and negative 2.080. And so just kind of like how we thought, our 6.131 lives all the way out here in the dark region. And dark region means we're rejecting. So reject the null hypothesis. Okay. So if we reject the null hypothesis, that means we're saying that we are not saying that there's no correlation. No correlation corresponds to this one. So it is not no correlation. We circle this one, which means that there is a correlation. So I'm going to say yes, correlation, which means our claim is true since our claim went with that one. So yes, there is a correlation. For some stupid, silly reason, chocolate consumption does increase your chances of winning a Nobel Prize. I guess one doesn't cause the other one. So the more chocolate that's consumed, the more Nobel Prize winners there are. That's the trend. Okay. Now, one more thing before I quit, and I better quit soon or I'm not going to be able to speak at all. One more thing is that if there is a negative correlation, instead of it being not equal to, this bottom one you're going to say is less than 0 because you're going to say that this value here on your list of where your R lives, if it's a negative correlation, it's going to be close to -1. If it's a positive correlation, it's going to be close to +1. So if in here it said to test the claim that there is a positive correlation, or that there is a negative correlation, then you would use less than for negative and greater than for positive. This one just said there is a linear correlation. It did not say positive nor negative. So we just do equal to, not equal to. Okay, so I hope that made all that sense. What I want you to do, you should be able to get all the way through number 4. Don't use this p-value because we do the critical value method. So you will need your correlation coefficient, R, and critical R, confusion. I don't know what your critical R is. Why are they giving that to you? Okay, so when you go down here, you should be able to get all the way through number 4. You don't use this p-value because I always use the critical value method. Your correlation coefficient they give to you. So this is the R that you're going to plug into your formula. And I'm pretty sure this critical R is the T that you get, but check that to make sure. So when you plug in the formula, check to make sure that this is actually what that is corresponding to. Okay? Try to get all the way through number 4. Number 5, they do not give you the value of R. So you might have to go and plug these numbers in. Actually, you know what? Just wait on number 5. Don't do number 5 until tomorrow. We'll do number 5 tomorrow, but go ahead and try number 6. You will have to plug these ones in to your Google Sheet and find the R value, and then you should be able to run the test like normal. So try to get all the way through number 4 and all the way through number 6. Okay, and number 6 is going to be a little bit harder, but go ahead and do the best you can. Okay.